teammates and colleagues from different teams at Microsoft towards improving code integrity on Linux. So I'm Sriram Nambakam. I'm a technologist and a Linux enthusiast. I'm currently serving as a principal engineer at Microsoft as part of the Azure Linux team. And I've been using Unix and Linux for a very long time, and I really like it. Prior to my current work at Microsoft, I've contributed a lot to open source as part of I've contributed to open source as part mainly in the realm of identity and security. I've been since 2005. I've contributed to the likewise OpenStack, which has been deployed on many Linux distros. After that, I've been one of the core contributors for the Lightwave stack at VMware, which was an identity stack. And as well, I've been a core contributor on Photon OS. Currently, I'm contributing to Azure Linux at Microsoft. So the work that I'm presenting today, I would like to call out several teams at Microsoft who contributed to this effort and to the community. And this is a work in progress, so some of the components are still being refined. As a cloud provider at Microsoft, we are constantly fighting security threats. And we want to learn from the community about what could go wrong, and we want to prevent it. And so what I'm going to present today is about improving the security posture of Linux in general. We want to contribute back to the community as well. We've taken, for our current, today, we are focusing on workloads running on Linux in Azure on OCI containers. So that's the scope that we are currently focusing on. In the future, we will expand that. So today, whatever I'm presenting is the basis for basically running OCI workloads on Linux. So as you might have seen, you must have heard of several exploits where people break out of privileged containers, and then they have elevated access to the system. That can lead to security breaches. So we've been looking at that area, and we want to protect the container host from such exploits. So if you look at Linux already, it has several features to safeguard the security, such as SE Linux, AppArmor. So they don't protect all the areas adequately. So in this talk today, I'm presenting an approach where we have secured the container host with SE Linux and AppArmor, but what about making sure that whatever programs are running on the host are what are expected, that is, people who have elevated access cannot change those binaries and impact the code integrity of the system and then execute those binaries. So not only for the host, we have extended this protection to containers as well. So now these users, they have access to their containers. But what if they change the binaries in those containers and then execute those? That is not expected. As well, there are some threats where you can copy a binary from the host into your container and then modify it there or run it from there in an unexpected fashion. So all of these are different exploits that we want to guard against. So this diagram, what we are seeing is the way we have designed the system. So over here, what you see, it's not very clear. Let me magnify that. So we are relying on trusted launch, secure boot, to make sure that the boot chain is secure for the VM that I'm showing here for the system. And so the firmware is verifying that in this case, so what you're also seeing here is we are using a unified kernel image because we want to make sure that the init RAMFS is also protected in addition to the kernel. And we are also protecting the root file system using dmverity. And therefore, there is a dmverity root hash that we have, which we provide to the kernel over the command line. And we also sign the dmverity root hash. So basically, in order to make sure that a potential exploit cannot modify the root hash, and basically we sign it, and we want to make sure all of those are protected. So we are using a UKI, a unified kernel image, to wrap it all up, and then we sign the UKI. So as part of the boot, secure boot, the firmware verifies that the UKI is signed using a key that it expects. And after that, as you can see, the kernel, once it comes up, the kernel is verified as well, and the kernel checks the root file system. In our case, the root file system is protected by dmverity, and therefore, the root file system is immutable in this case. So by making it immutable, we are ensuring that only verified binaries, only predictable binaries can be executed on the system. On top of this, we are showing, as I mentioned earlier, we are looking at OCI container-based workloads in this case. So you can see here how we have container D, and we have run C, and we have these OCI containers running. In this design, we are also we are showing the ORAS, which is the registry as storage, which is an NACR, actually. And we are verifying the signatures of all of the containers that we are deploying on the system to make sure even those are expected. And so basically, so in this case, we have achieved, by making this system, the main parts of the system immutable, we are preserving code integrity of the system. So now, we have also said that we are protecting the dmverity root hash, and that root hash is signed, and we are putting it all in the init RAMFS, and we have included that in the UKI, and that is also signed. So all of this is protected, the entire chain. As you can see in this diagram, we wanted to enforce dmverity. So it's not just enough to just protect all of these. So when a binary is run on the system, we want to make sure that that binary has the provenance to something. Either it should come from a file system that's protected by dmverity, or it should be protected by fsverity, or it should come from the init RAMFS, which we have already protected in the boot chain. So by making sure, so we want to have this enforcement. And the way we do it is when someone executes a binary on the system, the kernel is going to, so we have two Linux security modules in this system, SC Linux, and the other one is IPE. So IPE is going to help us. So this is integrity protection enforcement. So it is a Linux security module that is loaded into the Linux kernel. IPE was created at Microsoft. It has been accepted upstream in the 6.10 kernel. And IPE leverages the immutable system properties. So essentially, when you run a binary, it'll make sure that the inode, so basically it checks if that file that is being executed, the binary, is coming from either dmverity protected partition, or if it is coming from a fsverity protected file, or if it is coming from init RAMFS. So essentially it will check, it will establish the provenance to one of these areas. If it doesn't fall in any of these areas, then it denies execution. So it's an enforcement mechanism. And IPE, it checks the signatures as well of the files. And it is governed through a policy, which is provisioned through SecurityFS. So essentially, it protects from the user executing tampered file system components. So this is a sample IPE policy. So as you can see, the default action is allow, but then the next thing, we are indicating for execution, the default action is deny. But if that component is boot verified, which means it is coming from the verified initramfs, or if it has a DM verity signature, then we allow the execution for that. These are the exceptions. And any read, we allow by default. IPE has many more capabilities, but for a sample, I just chose these. Yes, please, go ahead. Do you want this? Yeah, I have a demo. I'll show you. Basically, you'll get a permission denied. It's e-access. Yeah. So I'm going to show a demo now. Actually, is there a holder for this? So here, what I have here is an image that's mastered using the design I showed here. Pardon? Oh, sorry, hang on. I think I need to. I will come back to this. I'll resume the presentation once I finish with the demo. So over here, what I have is, I have an image which has been mastered using the design I showed earlier. So where we have all the components being protected with DM Verity and with IPE. And so I have it running as this VM here. And then I have a Fedora VM here, in which I'm running an Nginx server, because I want to get a binary from there, which is, I'm going to add that binary onto this protected host, right? So now if I go into this here, so let me see, it's easier if I just use a terminal. Yeah, just a minute. Is that better? Oh. No. to, sorry. Is this easier to see? Should I change the background color? Sorry, I didn't expect I didn't expect this color. Okay. Cool. Is there a color scheme that someone knows would work better? Whoa, this is even worse. I think we'll go with this 172.17.212, 172.17.91.212. So what I have here, so if you look at this, So I hope you can barely see it. I don't know how to adjust this even more. I can go over it and show it again. Okay, sure. So just to make sure that we are, so if I touch user bin ls, it'll say it's a read-only file system. And basically we are protecting its DM verity, so this is expected. And now what we are going to do is I'm going to run up a container, and I'll explain this. So I have this, I'm going to say bash. I'm going to say /run container.sh mcr.microsoft.com/Azure Linux /base/nginx :1 nginx -27, let's say. Oh, sorry. So let's try this again. So before we do that, I want to show you one more thing. So I want to do a curl and HTTP. What's my other VM? So I'm going to bring down a binary. Oh, sorry, here. Yeah, I need, this has a stand, it'll be good. So what I need to do is I need to bring down the binary from my other VM into this. So this is 172.17.91.171. So what we will do is 172.17.91.171/hello -o hello. Okay. chmod +x hello. Now I'm going to run this hello, and I'm getting permission denied but we have to see what is causing this permission denied, because it could be my SE Linux policy which is blocking it, because I have SE Linux also set to enforcing. And so for the purposes of this demo, what we are proposing here is a defense in depth, which means we have multiple layers of security defense. So I want to put SE Linux temporarily into a permissive mode, just to showcase IPE. I mean, we don't intend to do this in production, but so set enforce 0. So now if you look at SE status, it shows that it's permissive. Now let's try to run it again. Still permission denied. So who is causing this permission denied? So now let's look at, I want to grep for IPE in var log audit. in the warlog audit.log, and over here, you'll see that IPE op is execute, action is denied. So IPE denied it from executing. Why? Because the binary we downloaded, it is not protected by DM Verity. So essentially, it looked, the LSM, it checked if it was supported, if it was protected by DM Verity, so it looked at the inode, it looked from which file system block it's coming from, it computed the root hashes all the way to the root block, it found the root hash, and then it compared the root hash to what's given to the kernel, and it didn't match. So therefore, it denied it. Now, let's imagine, just for curiosity, I want to disable IPE and see what happens. Right? So echo 0 greater than sys kernel security IPE enforce. Right? So now I have disabled IPE now by putting 0 in there. Now if I try to execute it, it runs. Right? So IPE was blocking it. But before we disabled that, Azure Linux was blocking it. Now let's try the next thing, right? So now let me show that we are protecting the containers as well. So now I want to, let's leave IPE disabled like this for now. And now I'm going to deploy the containers. So I'm going to now say CRICTL. Sorry, not CRICTL. I'm going to run this container. So I'm going to say bash run container mcr.microsoft.com/Azure Linux /base nginx :1 nginx 20. I just have to give a number. Oh, what is that? Okay. That's interesting. Okay. Well, so I'm running up the pod using cryctl, and I'm trying to deploy nginx from mcr.microsoft.com. And so now if I do crictl ps-a, you can see that the container is running. It's the nginx container. So now if you go, I'm going to go into that container. And now I'm running ls. As you see, ls works. And now what I'll do is I'll copy /user bin ls into /temp. And then I'm going to run /temp ls. Hey, that also worked, right? So now let's go back and turn on IPE. 1 greater than /sys kernel security IP enforce. Then I want to, after enforcing IPE, I want to go back into the container. And now I'm going to run /temp/ls. And it says permission denied. What about user bin ls? That still works. Because user bin ls, that inode was what we computed the root hash for when we composed that container. So we took the Nginx container, and we, using a program, we just took each layer, and we computed the root hash for that layer. We signed it, and then we put it all in a manifest, which we gave it to, so we implemented our own snapshotter. It's called the tardev snapshotter. And so the tardev snapshotter has the logic to associate these container layers with dmverity. So it's protecting the container layers with dmverity. So when we try to execute a binary from inside the container, it is IPE, which is running in the kernel, is protecting the host as well as all the containers. So basically, it's the same kernel module that is governing all these locations. So therefore, it is checking for dmverity. IPE is checking for dmverity even when we are trying to execute a binary from inside the container. So what we have done is we are not only protecting, so IPE is an enforcement mechanism. And we are using that to not only protect the host, but also all the container layers. So that's what we have achieved in this process. So in this case, I'm using CRI-CTL. I've tried to copy the binary. I could copy it with Docker CP, but with CRI-CTL, it's not straightforward without a CNI. So I didn't want to disturb my demo, but if we copied the binary from the host into that container, and we tried to modify basically a binary, that also will be rejected from execution. So I'm going to go back to my slides. So in the demo that I showed, I showed IPE in action. So we downloaded a binary, and we showed that it failed to execute on the host. And we tried to move a binary to another location inside the container, and we showed that that also failed, right? So this shows how IPE works and how it protects the system, and essentially, specifically for containers in this use case. So there are, so IPE is using keys a lot, because we are talking about signatures, we are talking about dmverity signatures. So, and customers have requested that they want to rotate the keys. So not only do we need to protect the system, we also need to find out how people can manage the life cycle of such deployments efficiently while keeping everything secure. So that's one of the research topics that we are exploring right now, about how to manage the keys. Because as I said, see, IPE is saying that the init ramfs is protected using the UKI, and we are signing the UKI. And basically, if you look at it in a cloud deployment, the secure boot leverages what is in the UFDB. And IPE has the logic to use various trusted keyrings in the kernel. So it is using the kernel's trusted keyring. It can also use the secondary keyring. It uses the platform keyring into which the mock keys are loaded when the system boots up. But there are some interesting issues that come in where if somebody wants to, let's say I want to bring a new container, which is signed using a different key, then how do I insert that key into the system? So using the secondary key ring, it's possible, because then I need to countersign that key using a key which is in the kernel's trusted keyring. That is one way to do it. So, I mean, these are all the nuances of, I mean, we are protecting it, but there is a cost associated, which is minimal, but we need to solve the entire thing to make it usable, because customers want the highest uptime that we can offer them. So, and also we are looking at seeing how we can leverage IPE. So in the system that I showed, what if somebody wants to bring a third party out of a tree driver, and during secure boot, is it possible, if we are loading it later, it's an out of tree module, then is it possible to wrap it in such a way that it can be mounted using dmverity and protected by IPE? So therefore, we don't need the distro builder doesn't have to sign that using their own keys. So that's a facility we are looking at. As well, we are also looking at key rotation, because that is the basis for IPE and dmverity in our use case. And this is where we are also looking at the community. If anyone has similar issues that they're trying to solve, that's an area that we can all benefit from. So we don't want to sacrifice security. We want to make it more, the life cycle better in this case. Did I miss a slide? Oh, here. Yeah. So as I said before, IPE depends on keys, and keys are hard to rotate without requiring a reboot, especially if you want to change the mock or you change the UFDB. When rotating keys, we want to minimize the provisioning time, and we want minimal fleet interruptions, and we want to streamline the reboots. And as you might have gleaned from this, whatever we are presenting is not just applicable to clouds, but also to edge. So this model is not new, but what we are providing, the new thing that we are providing is IPE, and the usage of IPE to protect container workloads. Because you see dmverity in Android, it's been there for a while. So we are leveraging some technologies and enhancing them further. So that's the value that we are bringing to Linux. And this is a pattern that the Linux community can use. So because IPE is open source, it's upstreamed into the Linux kernel. So I think this is a great value. And I have some references. There are docs for IPE. We are working on, actually, I need to, if I can go back from the presentation, I can show you some of the mechanics and come back to this slide. But I think, let me exit. I don't know of an easier way. So if I go back to this VM, so if you go into warlib container D, warlib. Where am I? Oh, sorry. hang on. I need to find out the background color for this. I think it should be white on black. I can make it larger. Oh, I'm in the container, that's why it's. So I go into warlib font. How can I make the font bigger? I think there should be a zoom, right? Somewhere. Change tab color. I don't want to change tab color. I want to change the background color. Control plus, okay. There? Is that better? Cool. So if I go into warlib container D, and I go into IO container D snapshotter V1, and I go into tardev. So I go into signatures, and I'm going to look at signatures format, JSON. So you see all of these containers for which we have computed, you see these containers, we have computed for each layer of the container, we have computed the root hash, and we have signed it. So, and then we have given that to our tardev snapshotter. So because I deployed, if you remember, I deployed this mcr.microsoft.com Azure Linux base Nginx. That's the container I deployed. And for that one, we have pre-computed all of these. For each layer, we have computed the signature and the root hash. And then we gave it to the tardev snapshotter. And so that when we do a Docker pull or a CRI-CTL create, it knows how to compute the what to expect for the dmverity hashes. And what we are trying to do, one of the things that we are trying to do is to streamline this flow. So we are working with ACR and seeing how when somebody injects the image, right at that time we can compute these hashes so that they're predictable. We are using Notary as part of this to check the signatures of the containers as well. So, I mean, that's work in progress that we have. So what I'm representing here is the work of many teams across Microsoft and the community. So big thanks to everyone to make this happen. So what I'm presenting here is the work of many people. Any questions? Yes. Here, you can take this.
Oh. Never know. Thanks. So this tardev snapshotter that you just showed, what is that? Is that like a service, like a daemon, or like it's a daemon? Okay.
We have specialized it for providing confidential containers in this case. So whatever I'm showing is open source. We are in the process of upstreaming it. And there's also a tarfs that we are using. As you know, tarfs is used by containers as a regular format. So that's another research area we are looking at to see what's more efficient. This is ubiquitous. Everybody is using tarfs. So we want to support that format, but we are also looking at something more efficient. So this snapshotter, the snapshotters generally are used for overlay. So as you know, the containers, they use different layers. And so on Linux, when you actually pull down a Docker image or an OCI image, which contains multiple layers, those layers have to be arranged as overlays. And there is a different snapshotter for overlay, which does that. And we needed to specialize that to leverage dmverity. And then we are using IPE on top of that. So
two more questions. Two more questions. So it looks like IPE depends on dmverity. Okay.
It is leveraging technologies which help preserve immutability. Basically, we want verifiability in an optimal way. So essentially, the dmverity algorithm, it provides a lot of an optimal way to make sure that that inode, that binary, has not been modified by using root hashes. We also use fsverity, but we are not. It supports fsverity, but we don't prefer fsverity because it's not as easy to manage.
Last question, I promise. So I noticed when you showed the link about the dev mapper, the tar dev mapper thing. It was part of the Kata containers project. So what's the relationship? Because you mentioned this is the like container D ecosystem thing. Is there some relation? I mean, I guess there is because it's in their repo.
It's related because Microsoft, our team, along with other teams, we developed this technology and we are in the process of upstreaming it. So basically that term is upstream. In this case, we are trying to open source it. So it's available on GitHub for anyone to look at what we did. So that way.
Yeah, thanks for the talk. Are you able to quantify the performance impact of enabling IPE?
We are in the process of doing that, especially in containers. So the IPE technology has been used in other areas in Microsoft already. So it's been used for many years. When we've upstreamed it recently, so we have also backported it to the kernel used in Azure Linux, which I was demonstrating. So we don't see, I mean, so far in our tests, we don't see any big performance hit, but we are still in the process.
Waving to friends. Yeah. No? Last chance. Going once, going twice. Sold.